Alright, in this video we are going to do a review for our first exam. Remember, the topics that we have looked at so far are events, sample spaces, tree diagrams, the fundamental counting principle, permutations, and combinations. By far, the most important thing with any particular problem that we're working on is the ability to recognize what strategy you should use. If you don't recognize that it is a permutation problem, it won't matter that you know how to use the permutation formula. Likewise, if you don't recognize that we have a fundamental counting principle problem, it won't matter if you know how to do it if you can't recognize it. At this point, I'm bringing up the calculator on the web that we'll be able to use. If you have a different calculator, like one of the graphing calculators or some other scientific calculator, you're free to use it. But we should get started. And I got to close this thing out. Don't need that. And then go. So here's our first one. Suppose that two 5-sided dice are rolled. Part A, draw a grid showing all the outcomes for the different totals that may occur. Well, we're asked to draw a grid with two 5-sided dice. So we have 1, 2, 3, 4, 5. This is the first die. Whoa, that's a terribly drawn line. But then we also have 1, 2, 3, 4, 5 for the second one. Since it's asking for the total, we just have to start adding them up. 1 plus 1, 1 plus 2, 1 plus 3, 1 plus 4, 1 plus 5. Continuing, 2 plus 1, 2 plus 2, 2 plus 3, 2 plus 4, 2 plus 5. 3 plus 1, 3 plus 2, 3 plus 3, 3 plus 4, 3 plus 5. And we can see the pattern that's developing. 5, 6, 7, 8, 9. 6, 7, 8, 9, 10. And this whole picture is what we need for part A. Part B asks us, use brackets, the curly brackets, to write down the sample space. Remember, a sample space is just the list of the different things that might happen. Looking at the grid, what are the different things that might happen? Well, we could get a 2, we can get 3, 4, 5, 6, 7, 8, 9, 10, but we cannot get an 11, we cannot get a 12, and we're finished. Our list of possibilities are the numbers 2 through 10. We don't bother to write down any kind of repeats. We don't bother to write down how many of them we have. We just write down one number for each different thing that could happen. Part C. Suppose a friend offers to play a game in which you are paid $4 every single time a number that's divisible by 4 is rolled. Otherwise, you pay your friend $2. If you decide to play, do you think you are going to win money or lose money? Well, we could look at each one of these different possibilities. Looking at the 2, are you going to win or lose? Yeah, 4 does not go into 2, so there we lose $2. Go to the 3, do you win or lose? You'd lose. Going to the 4, do you win or lose? So there you won $4 more. Going to the 5, do you win or lose? No, when we say divisible, we're saying it fits into it perfectly with no remainder. 4 does not fit perfectly into 5, so that's where we would lose $2. If we rolled this 6, do we win or lose? A 3, we lose. A 4, we win. The 5, we lose. 6, we lose. 7, we lose. Ultimately, what we've got to figure out is how many times can you lose, how many times can you win? Well, when we start backing these parts out, I'm going to actually backtrack this stuff and simply say, let's count how many times we lose and count how many times we win. Okay, so loses and wins. We know we lose $2 for every time we lose, but we win $4 every time we win. So a loss is 1, a loss is 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19. When we look at this grid, there are 19 different ways to lose, so we would expect to lose $38 there. But when we start looking at the wins, we have 1, 2, 3, 4, 5, 6 ways to win, which gives you 24. Do you want to play the game? Yeah, this is one where you would lose $38, but you win 24. So in the long run, you play the whole game out, it's expected that your buddy's going to take $14 from you. So if you decide to play, do you expect to win or lose? We expect to lose. And how could we use our grid to explain the answer? Well, we just did. This right here in the green box is the explanation. We would expect to lose 38 but win 24. That doesn't balance out in our favor. Number 2. The lunch at the diner has a choice of ham, turkey, roast beef, and you can have it on rye or wheat, and you could choose coffee or milk. Draw a tree diagram that would illustrate what a person might have for lunch if they pick 1 meat, 1 bread, 1 drink. You notice how they're saying 1 meat, 1 bread, 1 drink? This is telling us the levels of our tree diagram. In level number 1, what are the different meats that they could pick? They could pick ham. They could pick turkey. They could pick roast beef. Level 1 has 3 options. Level 2, and I'm going to change the color so we can see the levels, will be another choice. Now we have to choose the bread. You could choose rye, or you could choose white. And that choice goes for every single meat. No matter which meat you pick, you still have to choose between rye or wheat bread. That's our level 2 for the second choice. But we still have a third choice of what to drink. So with every last one of these pieces, we will need to branch off for a third level, a third color. Well, for that one, you could choose coffee or milk. We have the same choice. No matter what sandwich you pick, you still have the same choice of coffee or milk. And now we're done. The whole thing branched off. The black represents our choice for what could happen with the meat. Every single one of the meats branches off with the bread, because you still have to choose both. And after picking the sandwich, meat and bread, you still have the same choice of coffee or milk going over the whole piece. Our third question. Find the value for each expression below, show your work by hand, and use a calculator to verify your results. So, 5 factorial. How do you do 5 factorial? 5, 4, 3, 2, 1. And when we multiply all those things out, we can verify this with a calculator. 5 factorial equals, we got 120. And I'll switch colors for part B. Part B, and I'll match these up color to color. We had, I covered up the problem, 6. 6 permute 3. Well, do you remember the work? First number goes on top. 6 subtract 3 gives us the bottom. It just so happens that it's the same number. And so we'd have 6, 5, 4, 3, 2, 1 over 3, 2, 1. 3 on down would cancel, and we have just 6 times 5 times 4, which equals 120. We can go back to the calculator and type in 6 permute 3 and verify our work was correct. We still got 120. I'll switch to green for problem C. 7 choose 5. How does the combination formula go? 7 on top. 7 minus 5 is 2. And use the 5. Absolutely correct. So we'd have 7, 6, 5, 4, 3, 2, 1, 5, 4, 3, 2, 1, 2, 1. 5 on down cancels, which would give us 42 over 2. And 42 divided by 2 is 21. We can verify that with the calculator, though. So we'll type in NCR 7, 5, 21. We know we are correct. Progressing to question D. Okay, D is saying this piece. Why are there parentheses here? The parentheses are actually indicating, I know it's difficult to see, but it looks to me like they're saying it's 5 times 2 before you take a factorial. So yeah, that would be 10 factorial, 10 times 9 times 8 times 7 all the way down. We could then say, at the calculator, 10 factorial equals 3628 800. So 3628 800. 3,628,800. No, I used a calculator, man. The question was asked if I did 10 factorial in my head, and I'm not that good. There are people in the world who can do that kind of stuff in the head, but I'm not one of them. All right, for part E, we have 4 factorial, 2 factorial. What is this one saying? Yeah, do the factorial. 4 factorial is 24. 2 factorial is just 2. And so 24 times 2 equals 48. That is still another piece that we can verify with the calculator, because we can go and type in 4 factorial times 2 factorial equals 48. And we know we've done it correctly. So yes, this problem number 3, mostly, do you know the formula and can you verify with the calculator? Please note, the directions specifically state show your work by hand. If you're not showing this work in between, then you're not showing your work by hand. It would look like all you've done is use a calculator, And that's actually not following the directions. If you're not showing the work in the yellow boxes, you didn't follow the directions, and you can't get the credit because you did not do what was asked. Number 4, there are 4 runners in a race. In how many ways can the runners finish the race? We have several ways that we can do this one. The first way I look at this is to say you got 4 people who are running. So that's a group of 4. Does it matter the order they finish? That tells me this is a permutation problem. And how many people are actually going to run? That's 4. One way to do this problem is to recognize there is 4 people available. There are 4 people available, and all of them are going to run. So this is a problem where you would have 4 factorial over 0 factorial, which is just 4 factorial over 1, and that's going to give us the answer of 24. This is one correct way to do it. This is not the only correct way to do it. Another way that we can look at it is to say, somebody's got to finish first. Someone has to finish second. Someone has to finish third. Someone has to finish last. How many different people can finish first? 4. After someone has finished and won the race, how many are left to finish second? And then there were 2 left, and only 1 person can finish last. So if you multiply them out, you notice 4, 3, 2, 1 actually is 4 factorial like we had done right there. We could use the fundamental counting principle like we just did in Luke as well. We could use a permutation formula, perfectly valid. We could use the fundamental counting principle, another valid way to do it. For our 5th problem, a store has 18 outfits available. Okay, so 18 available, but only 6 outfits can fit the display at one time. In how many different ways can the 6 outfits be selected? Well, we're starting off, the pieces that you should recognize, there are 18 available, 6 of them will be put on display. We have to ask ourselves, though, is this a permutation problem? Or is this a combination problem? The answer to that is based on the question. Does it matter which one gets put in first? Yes or no? If the order is important, first, second, third, fourth, fifth, sixth, we have permutations. But if all that we care about is it's in the window, that's a combination problem. So which one is this? Do we care if it's all the way on the left or just it's in there? Yep, Clint said all we care about is it's in there. I agree, this is a combination problem. You notice how this thing does not say show all the work? Calculators are pretty awesome. Now that we've recognized this is a combination problem, we can go directly to say combinations, 18 are available, we're picking 6. Our answer is 18,564. The calculator gives us precisely what we need. It's pretty unlikely that the calculator will make a mistake because people who create calculators spend a lot of time in school learning how to do good computer algorithms. There is actually a college level class called numerical analysis. And in numerical analysis, they teach you how to do computer programming so that calculators don't make mistakes. Is it possible that a mistake still could be made? Sure. But you're kind of trusting the fact that whoever created the calculator knew what they were doing. And if you don't trust them, then you can do 18 times 17 times 16 times 15 and do all that stuff completely by hand if you don't want to trust them. Number 6. Paul has 3 baseballs and 4 bats. How many possible ball and bat combinations can he choose? This is a piece that's a little bit tricky. It says the word combination. That does not make this a combination problem. It doesn't even make it a permutation problem. This is one that's probably done easiest by simply saying he has the baseball and he has the bat. We can use the fundamental counting principle to get our answer. How many baseballs does he have? How many bats does he have? Just by recognizing the slot for a ball and the slot for a bat, we can set up the fundamental counting principle to find the number of possible pairs. 4 times 3 gives us 12, and we're done. Recognizing this as a fundamental counting principle problem is really the most important part of it, because if you don't recognize the strategy, you're not going to be able to do the really easy 3 times 4. So here we go. How many license plates are possible in Minnesota if each plate must have 3 letters followed by 3 digits, and things are allowed to repeat? So what we're noting is letter, 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 followed by number, number, number. That's the format we have to have. How many letters are available for each spot? Yeah, there are 26 letters in the alphabet, so we can have 26, 26, 26, because we are allowed to repeat letters. For the digits, we have 0 through 9. That's 10 digits, so they can be repeated. Multiply that out, we have our answer. Go back to the calculator to save us some time. 26 times 26 times 26 times 10 times 10 times 10. 193,336. Did I? Nope, I don't. 193,366,000. The question that was raised is, did I put in an extra 0? Of course, if you're watching on the video, you can backtrack and look at the screen and see that I had 10 typed in 3 times. But what I'm recognizing is, since I'm multiplying by 3 tens, my answer should have 3 zeros at the end. And it does. Yeah, kind of a lot. Minnesota could have 193,366,000 different license plates. North Dakota, by the way, follows the same convention. So North Dakota can have the exact same amount. That doesn't even allow the possibility of personalized license plate, which makes it even more. So, same problem. But how many license plates are possible, but you can't repeat? But we still have the letters 26, 25, 24. And then we have the digits 10, 9, 8. Well, we'll run over to our calculator, multiply those out. 26 times 25 times 24 times 10 times 9 times 8, which gives us 11,232,000. Yes. So there we go. Still, a lot of license plates available, even if you don't allow repeats. Continuing with our next question. There are 20 candidates in the Mr. Minnesota contest. How many ways could the judges choose the winner, first runner-up, and second runner-up? Well, we should recognize there's a group of 20. And we're looking for winner, first runner-up, second runner-up. That's a group of 3. Is this a permutation or a combination problem? This is permutation because who finishes first is important to the people in the competition. Well, just running over to our calculator now, 20 permute 3, NPR 20, 3, 6,840. And we'd get our final answer. Moving on to the next one, number 10. The yearbook editor must select 2 photos of 42 juniors. So from right there, we can say 42 juniors, we're picking 2 of them. And 2 out of 45 seniors. So we have 45 seniors still getting 2 of them. How many photo combinations are possible? Well, is this a combination or a permutation problem? Do you care? Does it matter if you're the first person picked versus second person picked? No, because you still get, if as long as you're one of the 2 picked, you go in the yearbook. That's why it's going to be a combination problem for both of them. But there's still one more really important clue that we have not yet discussed. This word. We're picking juniors and seniors. This is an and problem. Remember, and problems are multiply, or problems are adding. So we can run right through this whole piece. I'll type the whole thing here into our calculator. NCR, 42 juniors, we're choosing 2 of them. And for multiplication, we're picking or choosing 45 seniors, picking 2 of them. Click equals, and we have our answer. 852,390. And so there we go. We have our final result. Continuing to our next problem. A homeless shelter has decided to purchase all new kitchen appliances. They need an oven, they need a fridge, and they need a dishwasher. The store has 7 brands of ovens, 6 brands of refrigerators, 5 brands of dishwashers. In how many brand arrangements can they purchase their appliances? Do you recognize this as a fundamental counting principle problem? Oven, fridge, washer. So 6 ovens. I'm sorry, I had that backward. 7 ovens, 6 fridges, 5 dishwashers. 7 times 6 times 5 equals 210. Recognizing the fundamental counting principle is perhaps the toughest part of this particular problem. Number 12. An ice cream shop has 8 different flavors of ice cream available. How many 2-scoop cones can be made if you're allowed to have the same flavor for both scoops? We should recognize this one. We have the first scoop. We have the second scoop. How many are available for the first one? Well, there are 8 flavors. And how many are available for the second one? Still 8, because you are allowed to have the same. You are allowed to repeat it. If it was not allowed to repeat, then we'd have to go 8 times 7. But this gives us 64 different types that you could possibly have. Problem 13. An ice cream shop has 8 flavors, but now you have made the decision they won't be the same. Pretty similar to what we just did and what I was just talking about. Scoop 1, scoop 2, 8 available, but scoop 2 is different. So we wind up with 56. The important characteristic here is recognizing this as a fundamental counting principle problem. We can see the numbers 8, we can see the numbers 2, and that might lead a lot of people to want to do a permutation problem. It might lead people to want to do a combination problem. These might work out, they might not. We can actually punch these into the calculator to see if they work. 8 permute 2 gives us 56. If the order is important, this basically falls into a permutation problem. But if we went 8 choose 2, we get something that's way different. So you may remember one of our learning objectives, the fundamental counting principle and permutations are actually related to each other when you don't repeat stuff. If you don't repeat stuff, permutations and the fundamental counting principle are actually the same thing. Number 14. Suppose a jury is being selected from a pool of 20 candidates. How many ways can it be done? So we have 20 to pick from. We're going to pick 12. Does it matter who gets picked first? No, not for a jury because everybody votes the same. This is a combination problem. Recognizing that the order is not important is one of the critical components. So we'd have combinations, 20 picking 12, and there's our answer. 125,970. 125,970. Our next problem. Suppose a jury is being selected from a pool of 13 men and 7 women. How many ways can this be done if the judge states that the jury must contain exactly 5 women? So please note, we have to pick men, we have to pick women. In this regard, we have a fundamental counting principle problem. But how we pick the men is going to be another combination problem. Well, if there are 5 women, that tells us there have to be 7 men, because the whole thing adds up to 12. 7 plus 5 gives us 12. Well, there are 13 men available. 7 of them are getting picked with combinations, because it doesn't matter which order. There are 7 women available, and exactly 5 are getting taken. Just by multiplying these two combinations, we will be able to get our final result for exactly 5. So let's come over. 13 choose 7 multiplied by 7 choosing 5. You'll note the structure is the same as what we had written on the smartboard. 13 men, 7 are getting picked. 7 women, 5 are getting picked. Altogether, 30,036 different possible juries. 36,036. Okay, so we're going to back up, or rather continue. Number 16. We're still picking this jury. But now we are saying the jury must contain at least 5 women. Well, this one, I freely admit, is going to get very, very big because we have to set it up if there are exactly 5 women, if there are exactly 6, exactly 7, exactly 8. Please tell me why exactly 8 doesn't matter. How many women are available? So can you ever put 8 women on the jury when there are only 7 available? Can you put 9 women on the jury? 10, 11, 12? All of these with exactly 8, because there aren't enough women, we know that can't happen. Well, we have to put these 3 pieces together. If we know, based on the last problem, there are 36,036 available ways to do it with exactly 5 women, we can do something similar for exactly 6 women. If we're going exactly 6 women, there's 13 men available, 6 are getting picked. There are 7 women available, 6 are getting picked. We'll plug this piece into the calculator to figure out how many ways we can have exactly 6 women. So 13 picking 6, and 7 picking 6 for our combinations. Just typing in what I had on the board, there are 12,012 ways to get exactly 6 women. Now, how many ways are there to get exactly 7 women? Well, there are still 13 men, but if we pick 7 women, that means there are 5 men, and it means we're picking all 7 women. So coming back to the calculator, 13 men picking 5, 7 women picking 7, and when we multiply that out, 1,287 ways to get different juries with exactly 7 women. So we have exactly 5, exactly 6, exactly 7, and we know for exactly 8, 9, 10, 11, 12, there are none, because there aren't enough women. This is a problem that hinges around the idea that you recognize at least 5 is the same thing as saying exactly 5, or exactly 6, or exactly 7. Because this is an OR problem, it tells us it's an adding problem. 36,036 added to 12,012 added to 1,287. You add those all up, we have our answer of at least. So 13 plus 2 is 15. 11, 12, 13, 3, 6, 8, 9, 4. And there we go. There are 40,000 or 49,335 different juries that could possibly be created that contain at least 5 women. Problem 17. In how many ways can I put together an outfit if I have 7 shirts, 5 pairs of pants, and 4 hats? We have shirts, pants, hats. It's a fundamental counting principle problem. So we've just got to take 7 times 5 times 4. That's 140. And we're done. And our last problem. For $7.99, a restaurant will sell you their lunch special. The special is a choice: hamburger or chicken, onion rings or fries, soda or coffee. Part A, make a tree diagram. Well, we have hamburger or chicken. Then, choice number 2, onion rings or fries. Then, soda or coffee. Here's our part A. We have our tree diagram. Part B, how many different answers or how many different outcomes are there? Use the fundamental counting principle to justify your answer. Well, we have the choice of sandwich, fries, or the drink. 2 choices for the sandwich, 2 choices for the type of fry, 2 choices for the drink. There are 8. And we could even get that full list. 1, 2, 3, 4, 5, 6, 7, 8. So, having looked at these 18 problems, we'll go back to our learning objectives for the day. We've reviewed events, sample spaces, tree diagrams, like the grid even, fundamental counting principle, permutation, combination. We've talked AND problems, we've talked OR problems, we've looked at all those different components. Those are the things that we need to be able to do for our exam.
I don't even think I can remember all that.